The last time I gave this talk, it was in front of a group of a bunch of theorists, many of whom were quantum gravity specialists. And as far as I can tell, they didn't like it one bit. I ascertained this because mine was the first talk at the conference, and then for the rest of the week, people kept coming up to me telling me how much they disagreed with my talk. My sense is this is a slightly friendlier audience, so we'll see. I'm an experimental physicist turned observational astronomer, and with a long interest in gravity, though. And in my declining years, I've decided to indulge myself with that interest. So to start with, let me pull this out. To start with, let me tell you about two things that motivated me in a broad sense, two things that have bothered me for a long time. One, I'm sure, is something that everybody has worried about at one time or another, and this goes all the way back to graduate school, and it was the measurement problem, or collapse of the wave function. For me, I always express it as quantum mechanics is this great theory, and it has all these wonderful predictions, but it never lets anything happen. Nothing ever happens. I mean, Schrodinger's cat is in this mixed state of alive and dead, and nothing else happens. You just have to decide when it is. And the reason this will come into gravity is because I'm sure it's either the dead cat or the alive cat that's the source of gravity. It's certainly not both of them. So that's one thing that's bothered me. The other one was something that it was far more recent, and that is, dates back to almost the same time. As a graduate student and as a postdoc, I helped design and build a cryogenic gravitational wave detector. So I was giving talks, and a lot of popular talks on gravitational waves. And invariably, I would just draw the analogy. I'd say you take a charge, you shake it up and down, and you emit an electromagnetic wave. Well, the same thing is true. If I take a mass like my fist and shake it up and down, I emit a gravitational wave. And I knew it wasn't much, so then I computed it after giving this talk a few times, and of course it was just a 10 to the minus some big number watts that I was emitting. And then a few years later I thought, I wonder how many gravitons I'm emitting. So I took the h nu, divided it by that power, and it turns out that shaking my fists like this emits 1 graviton in 1,000 lifetimes of the universe. So in fact, I'm not emitting anything at all. And that bothered me because here, this is a perfectly well-defined macroscopic mass. You'd think Einstein's equations tell you what's going on, but if there's such a thing as quantum gravity and a graviton, no, nothing's going on.
So that's because your frequency is very low?
My frequency is low and gravity is very, very weak. So then about 8 or 10 years ago, I was sitting at a colloquium getting ready for a talk. I came a little early. Freeman Dyson came in and sat down beside me, and for some reason we started talking about gravitons. And Dyson said, you know, I've been thinking about trying to design a hypothetical experiment to detect gravitons, and nothing I can come up with. It's orders and orders of magnitude away. It's just impossible to do it. And then, as Dyson often does, with a twinkle in his eye, and says, and if we can never detect them, maybe they don't even exist. Well, that's all it took. I immediately started working on a little back of the envelope calculation. Didn't hear a talk at all. And this was the calculation that I did. I assumed 1 graviton was incident on an ensemble of resonant mass gravitational wave detectors. That's all I knew, right? I knew the cross-section of it. And I assumed you could focus it down so that it was a single graviton that had a dimension of some size r. And then I just started packing that radius with resonant gravitational wave detectors and asked how much mass did I have to put in there until I could be assured that I detected that graviton in one of them. Well, it turns out that the size of that sphere of graviton, of the gravity wave detectors, with Schwarzschild's radius divided by times the speed of sound in the detector divided by the speed of light. And Steve Carl referred to that earlier. that's a single graviton detector, but to detect it with any kind of reasonable probability at all, it had to be inside its own Schwarzschild radius, which is disruptive to say the least. So then I told that to Dyson after the talk, because he listened to the talk, and he said, well, that's not what I had in mind at all. I was thinking more of atomic processes. So anyway, that got Tony Rothman, a friend of Freeman's and mine, who was also interested in it, and we started calculating the interaction of high-frequency gravitons with hydrogen atoms. And of course, my previous Gedanken experiment was just detecting a single graviton with high probability, but quantum mechanics is a statistical theory. I just need to detect some of them, right? I mean, and so we found out that in principle, you can detect a small fraction of incident gravitons, but when anything remotely resembling realistic physics comes into play, you can't do it. No one will ever do it. I can say, you never say never, but I can say safely that no one will ever detect a graviton because, I mean, these were the kinds of things that we came up with. I think a Jupiter-sized silicon matrix filled with hydrogen, because that's what we did our calculations, with a radiating Hawking black hole in the center of it. And that detector could detect, in the lifetime of the universe, 1,000 gravitons. Now, that's what I mean. In principle, maybe, but really not possible. So then I started thinking, well, why do we need a quantum theory of gravity in the first place? I mean, there's the usual unification argument. If you're going to unify gravity with the other three forces of nature, and they're all quantum theories, why gravity surely has to be a quantum theory as well. But me being an experimentalist, I thought there's absolutely no experimental or observational evidence for the quantum nature of gravity. And because there is no evidence, maybe we ought to at least consider that. So it's not a new idea. As Steve Carlip just pointed out, that for a long time, Rosenfeld, Christian Muller, and I put Steve's name on there as well because his was the most recent paper I'd read about it, that suggested this semi-classical theory of gravity where the Einstein stress energy tensor is replaced by the expectation value of some quantum operator. So nothing is new. And also there was yesterday, Manali Derek-Shani, I don't know if he's back there. Well, there he is, had a poster essentially on that as well. So non-quantum gravity is nothing new. In fact, it was, when I read Steve Carlip's paper, Is Quantum Gravity Necessary? That's what really inspired me to write down my thoughts, and I don't think I ever would have written the paper I indicated on the first page had it not been for Steve. So here's my non-quantum conjecture. I sent an earlier draft of my paper to Carlip, and he, where I suggested that if a system was completely quantum, a coherent, non-localized, say, matter wave, that there was no gravitational field at all from that. So it wasn't only non-quantum, there was just no gravitational field at all. And Steve was kind of said, well, why do you say that? I mean, that seems like it's an awfully silly thing. So I did back off, and I said, in order to have a well-defined gravitational field, you have to have a well-defined classical localized stress energy tensor or mass density. If you can't define, if you can't tell me where a particle is, then the gravitational field of that particle, I conjecture, is not well defined. Don't even have to talk about it. And then, of course, by extension, as Steve pointed out earlier, I implicitly assume there's no such thing as a graviton. Okay, so then the question was, what are the consequences of that kind of a non-quantum conjecture? And I'm going to show you a Gedanken experiment in a minute. Sure.
I apologize for interrupting.
Oh, that's okay.
What you just said is if the mass is not sufficiently well localized, then there's no gravitational field. But you're saying that an electron would not have a gravitational field?
Right, right. Unless it was localized. If you
well, I mean, you never know precisely where the electron is.
Well, when it hits a phosphorus screen, you know where it is.
Within a radius of uncertainty.
Yeah, yeah. And that could define a gravitational field to within that extent. And so in other words, if it isn't well defined, forget about it. If it is well enough defined, you just use Einstein's equations or some classical variant of that. Okay, so then what I found out, and you're going to see in this Gedanken experiment in just a minute, that in fact this non-quantum conjecture that I have, in microscopic systems it has absolutely no consequences at all, because gravity is in principle undetectable in microscopic systems. In macroscopic systems, stress energy tensors or mass densities are always well defined. And then Einstein's equations are quite okay. So that leaves open this in-between mesoscopic area where possibly you could figure something out. Okay, let's see. So consider this Gedanken experiment. And all the calculations I did, I didn't even pi's, square roots of 2, all that's gone. These were just dimensional numbers. So these are really back-of-the-envelope calculations. So I assume that there's a mass in a momentum eigenstate, a mass m, that's incident on a double-slit plane, and you get the usual double-slit diffraction pattern. But then, right in front of in between the two slits, I put another mass, which I'm going to monitor all the time as a test particle, and to see if I can measure the gravitational field of this coherent quantum state, and because I claim that it doesn't have a measurable gravitational field. It turns out, and the only conditions I put on it are, well, the two main conditions I put on it is that the momentum has to be large enough so that you can actually see a diffraction pattern, and 2, the effect of that mass on the test mass has to be strong enough that you can detect its motion of the test particle within the uncertainty principle. So that's the only thing. No experimental things at all. The net result, and then there are a couple of other equally reasonable conditions, and it's those other conditions that actually say that making those two masses the same value is the optimal situation. So here's the result of this back-of-the-envelope calculation. What I was hoping was that it was, and I don't know why I was hoping it was going to come out that it had to be bigger than a Planck mass, because after all, but I should have known better. There was no velocity of light at all in this experiment, so it doesn't come out that way. And so in fact, those are the conditions I have. And none of those put a condition on the mass because there's two unknowns. R is the slit separation, T is the time of the experiment, A is the acceleration of the test mass, and V sub I is the incident velocity. And you can't draw any conclusions from that. But now I add just one more reasonable constraint, and that is that T has to be less than the age of the universe. You've got it. So I put that in, and then you can evaluate all of those things. The mass has to be larger than 10 to the 7th proton masses, has to be bigger than 30 meters, and then these outrageously small accelerations and velocities. I mean, absolutely not possible to detect. I do point out, because of the large power of the mass in that time inequality, it's not overly sensitive to time. So if you reduce t all the way down to 1 second, you get actually only 3 orders of magnitude larger, now 3 times 10 to the 10th proton masses, and these are all the same now because it's 1 second, 2 times 10 to the minus 7 centimeters, or centimeters per second, or centimeters per second squared. This is still an outrageous experiment that I don't think, is beyond any kind of reasonableness. If you put that mass with this velocity, it's an equivalent temperature of 10 to the minus 11th Kelvin. But again, because that power of that mass is so high, if you allow that mass to go up to 10 to the 13 solar mass, you see I'm an astronomer, 10 to the 13th proton masses, the equivalent temperature is 300 degrees Kelvin. So it's still firmly in the mesoscopic scale. If you actually let V equals C in the previous thing, all of these values come to their Planck masses. So I say the mesoscopic, for me, the mesoscopic range is between, say, 10 to the 12th and 10 to the 19th proton masses. Okay. And the large, as Steve had in his slide too, as far as I know, the largest mass that has where people have diffracted it is Buckminster fullerene, which is around 1600. So we're still a long ways away from these 10 to the 10th or 10 to the 12th, 10 to the 12th masses. So a looming issue, whether or not this experiment can ever be done, a looming issue is conservation of momentum, because I'm saying that I'm conjecturing that this classical test mass is not attracted gravitationally by this incident coherent non-local wave, but you know the other way around is absolutely true, that a classical mass absolutely attracts a coherent wave. I mean, the equivalence principle demands it, and the Pound-Rebke experiment actually detected it. So there's the Pound-Rebke experiment where they shot a gamma ray from, I think, a 20-meter tower, and sure enough, that gamma ray increased its momentum as it fell in the Earth's gravitational field. Now, if I'm saying that the Earth was not attracted by the gamma ray, then the Earth wouldn't have any recoil momentum at all. Its momentum wouldn't be changed. Now, it's not going to surprise you that there's no way in the world you're ever going to measure the Earth's momentum change with a single gamma ray. In fact, that violates the uncertainty principle if you could measure it. So I'm going to have to increase the mass of this gamma ray, or this coherent wave, decrease the mass of the Earth until I actually can detect it. And wouldn't you know it, you get exactly the same four relations as before, as with the double slit experiment. So it's exactly the same thing. So the question remains, is momentum conserved? Can you conserve momentum? Now, a way out of this dilemma might be, well, now wait a minute. If I put a test mass there and I claim it isn't really affected by the coherent quantum system, well, maybe it is, maybe it isn't. But if I put the mass there, maybe that's equivalent to measuring detecting the quantum system, in which case, in ordinary language, the wave function of the coherent wave collapses, it becomes a classical particle, and then of course it will attract, because I claim classical particles with well-defined, well-localized stress energy densities are the source of gravity. How this happens, how that might happen, of course, requires a model. And I don't have a model at all. So I mean, this is just a loose conjecture to get people to maybe consider this possibility. But you might consider doing a decoherence type calculation between a localized particle and a plane wave, or in the double slit experiment. That's a little funny because decoherence experiments treat both systems quantum mechanically. There is I was pointing out to one of the participants here, there is a set of papers by Hall and Reginato, which I don't know are well known or not, but they're not in the decoherence community, but they have a model of where they treat stochastically both classical and quantum systems, and so have I think a legitimate model for the interaction of classical and quantum system that conserves probability, conserves momentum and energy, and that would be an ideal way to do such a calculation, to just see how in fact gravity might interact in that model. And I'm actually loosely collaborating with Marcel Reginato to do it. A test like this, though, even if we do such a calculation, is I would guess, decades in the future, if it's possible at all. I mean, we're talking about coherent systems that have 10 to the 13th proton masses, and nothing close to that has happened. I mean, there are macroscopic coherent systems like superfluid helium and superconductivity, but those all have well-defined stress energy tensors. Let's see, what else was I going to say? So non-quantum gravity among most theoretical physicists, as Steve pointed out, is tantamount to heresy. But I think probably the real heresy is the fact that I want to treat classical particles as real objects in fundamental physical theory. I think that most people would rebel against that. Classical physics, everyone says, is just the limit of some quantum theory. I've always found that a little curious, that this great need to unify all of physics is there. There's a perceived great need, where still, in some sense, unifying theoretical quantum physics with classical experimental physics, that unification doesn't seem to be so great. I mean, if you can't define anything classically, as far as I know, quantum mechanics doesn't even say anything. It needs classical physics, or at least experimental physics, statements about experimental physics, to actually make any predictions at all, to give the theory meaning. I can talk about that more later. As for the reality of classical objects, I really do think I'm here and not in some mixed state, the one that didn't come to the conference and is back in my hometown. And as I said before, I have no doubt that it's the live or dead cat of Schrodinger's that's the source of gravity, not some mixed state of that. So why should gravity be so different? I mean, Steve also mentioned that. Gravity is different in a number of ways. I mean, it's phenomenally weak. It's inherently global in nature. You can always make gravity go away if you jump into a local inertial frame. And it acts, it acts on everything else. It couples to absolutely everything. So the way I kind of look at it, this isn't any deep thought. The way I kind of look at it is there's the classical world that generates gravity. Gravity performs the background of space-time, describes the background of space-time, the quantum mechanics in which it resides, and then quantum mechanics makes predictions about classical experiments. I mean, no such thing as a quantum experiment. And so, in some sense, I think that that's not necessarily a bad picture. We may yet come up with a mathematically consistent quantum gravity theory, and if I had to bet, I maybe would bet that was going to happen. But if we do that with absolutely no observational consequences, for me that would be a really a hollow victory in some sense. And again, it's me talking as an experimentalist. I'm going to end with a quote also by Rosenfeld. Another one that he said, and I'll let you read this. It's a caution by Leon Rosenfeld back in the 1960s. And I'll just let you read that. Thank you.
You said that you think the cat being alive or dead will gravitate, but it will not gravitate if it's in the superposition or some mixed state.
Well, no, mixed state is fine because I guess I don't believe there is such a thing. It's a classical object, and it's either one or the other, and not both, and that doesn't contradict quantum mechanics as long as it's hopelessly entangled with its environment, which it undoubtedly is.
But so you would then, I assume, disagree with Roger Penrose's proposal that a mass in some superposition state will gravitate, and therefore there will be some self-energy due to the mass being these two states. And
Yeah, I mean, I disagree. I mean, it's just this is not that model. I mean, that could be I mean, that's in some sense that's a decoherence, a mechanism for decoherence, an intrinsic mechanism for decoherence, and I guess I have no problem with that. And because I don't have a model or a theory, it doesn't contradict anything I say, I don't think.
Has anybody thought of the following experiment in a different arena? You can look at particle, high energy physics processes which use missing energy, okay? And missing energy can be neutrinos, other fictitious supersymmetric particles, but it could also be gravitons, and gravitons have the unique characteristic that they're a spin 2, they carry waste angular momentum. It seems to me that one could look for a test of gravitons by simply looking for kinematic configurations that would only be accessible to the emission of a particle of spin 2. It seems to me this is a more or less unambiguous experiment. K like K goes to pi plus graviton has straightforward kinematics, it's two-body final state. Has anybody talked about doing such an experiment?
I don't know. I suspect so, and I imagine that would be absolutely wonderful. It's just that you would never. It would be like the initial neutrino predictions. That you just assumed something was taking something away, which is fine, and then neutrinos were eventually detected directly, and they not. And I'm claiming gravitons never will be. But even more than that, just the cross sections are so minuscule.
Everything's obviously hard. We're in a league where everything's impossible. But since people do these experiments, I'm just questioning whether anybody has worked out what limits would be from existing high energy experiments.
I don't think we did that. The more technical paper that we actually did, and we did this with linearized quantum gravity, was just to compute the 2p to 1 or the 3p to 3. Well, yeah. 3p to 2s transition in a number of different ways, and the time in hydrogen, and the time for that, believe it or not, is 10 to the 22 times the lifetime of the universe. I mean, these cross sections are absolutely enormously small.
Maybe last question, Professor Carter.
So first, a quick comment on the last question. People certainly have worked that out because there are these models of TeV scale gravity.
Yeah.
That's one of the main things people at the, one thing a lot of people at the LHC are looking for. So the cross sections and it's all worked out, and I don't know if anybody has actually sat down and looked at what happens if you go back up to Planck scale gravity, but it's just sitting there.
Okay.
My question or comment or somewhere in between, this is something probably I should have said during my talk too. There is one place where, at least in standard theory, there is a non-localized stress energy tensor that has very visible results, and that's in the very early universe in the standard inflationary model, where the fluctuation, the galaxies we see are supposed to come from quantum fluctuations of the inflaton field in its vacuum state. It's not that easy to produce that kind of Gaussian fluctuation if you're not in some pure quantum state. Have you thought about alternatives or what?
No, that's way beyond me, and I mean it's only that we're talking about times in the early universe when the density of the universe was 10 to the 80th times the density of a proton, and I don't have any confidence that that we know anything about physics at that scale. But the answer is no. I haven't thought of that at all.
Okay, then let's thank all our speakers for today.